This video is intended to explain how to use the Dynamics 1444 series application guide as an aid in determining and implementing monitoring solutions based on smart machine concepts. The guide will help to explain how Dynamics can be applied to make a smart machine. Smart machine technology, when built into the integrated architecture, can enable solutions that make machine conditions simply part of what you do. Presenting condition rather than simply vibration encourages very different behavior in operators, maintenance personnel, and management. Consider the difference in behavior if a high vibration alarm is presented versus the behavior if the indication was severe cavitation, moderate misalignment, or severe imbalance. And how does behavior change when responsible personnel can observe the propagation of these faults simply and easily using the same tools that they use to trend other common parameters such as load, pressure, temperature, or tank levels. Using these tools allows users to easily correlate vibration, or for example cavitation, with other process parameters. It may make something, such as a specific combination of valve position, tank level, or pressure in a particular operating pump, to cause that pump to cavitate violently. How would knowing this affect operations? How may it benefit the facility? So let's look at the guide. First thing to understand is that there are three major areas of the guide. There's the introductory part, which includes some important information that is used in the actual machine definitions themselves, and then of course the machine definitions, which talk about how to monitor the machines. And thirdly, it includes sections that provide ancillary but often very useful information. So let's look at the machines. In the application guide, machines are grouped as those fitted with rolling element bearings and those fitted with fluid film bearings. Now let's look at machines that are fitted with rolling element bearings. The list is broken down by the machines that are components of the larger machine. These are the drivers, typically motors, but perhaps turbines of some sort, and then the driven equipment, whatever it is driving, whether it is a pump or a fan or a blower or perhaps a gearbox. If we look at a specific machine, let's say a belt-driven fan, you'll see that the information in here includes monitoring requirements and the sensors and then the faults and the band limits and definitions and then the alarms that you might apply. And these are going to be the same regardless of the type of machine. They will all have the same kind of information. If you look at the details, the sensor and monitor requirements always come first. And this one is very brief. It simply says the fan is monitored with one or two general purpose sensors that are mounted at each bearing. Okay, so how do we understand what that means? The sensor requirements are actually defined in the bearings discussion. So where we talk about bearings, it will talk about the sensors that you have to apply and give you some guidance on how many to apply and where to mount them. So if we look at that, look under bearing type. In this case, we're using rolling element bearings. If you look over here, go down a page or two, you'll see that there's a discussion that says for machines up to 500 horsepower, one radial sensor per bearing is normally sufficient, normally mounted in the horizontal direction. So for the fan, coming back down here, you will simply mount one sensor, if it is a small fan anyway, under 500 horsepower, in the horizontal direction at each bearing location. The machine faults then are listed following that. This is a list of the common faults that might occur on the machine and the uncommon that are unusual but might occur, and well, unusual faults that are pretty rare. After the machine faults, the guide then talks about band definitions and limits. The band definitions are simply some guidance on how to set up the larger signal processing such as Fmax, the maximum frequency of the measurement. These will be applied to the bands, which we'll talk about in a minute. But in the section as well are the alarm limits. And this is talking about the overall alarm limits that are applied to the measurements that are made. Overall is a very common thing. It is for most machines how you monitor them and is the big guidance number that protection is certainly almost always based on anyway, and what standards are applied to. So in this example, it is telling me what the overall alarm limits are for this class machine. And it also tells you where these come from. It talks about ISO standards that are applicable to this particular machine. In this example, the ISO standards, there are two that may apply, 14694 and 10816-7. Those are actually listed in the guide as well. If we go back to general information, applicable standards, then scroll down to find 14694, a little too far. And there it is at the bottom, industrial fan specification for balance, quality, and vibration levels. So that's where if a customer wants, or if the user wants to get into the more detail of where the specification comes from, or what the number means, then that's the standard. This then is a list of all of the standards that apply and that are referenced in the guide. It's where the overall alarm limits that are stated throughout the guide come from. Following the band definitions and limits, we have the list of alarms that we would define. These are defined in terms of FFT bands. We talk about bands that you would define to monitor typically the common faults that we just talked about and how you would do it. So this example talks about how you set up 5 bands. The band 0 is going to monitor the unbalanced force. Band 1 is going to monitor for indicators of alignment or possibly looseness. Band 2 is vane pass frequency, and that is an indicator of turbulent flow. So you have a flow problem through the fan. Band 3 is bearing fundamental and lower harmonic frequencies. And band 4 is bearing higher harmonic and natural frequencies. If you have a bearing fault, typically band 4 will elevate first, and then as the bearing degrades, at some point you will see band 3 elevate. So in one sense, band 4 is early bearing fault detection, and band 3 would be an indicator of late bearing fault detection. After each band, it is telling you the frequency range that is used to define the band to monitor that particular indicator. It talks about percent of overall levels. This is talking about the maximum amount of energy in that system that this particular indicator should comprise. So imbalance, for instance, should be the dominant force, certainly, but not really ever more than about 90%. If it grows greater than 90% of the overall, then that might tell us that the unbalance is growing dramatically and become such a dominant element. If you have a badly unbalanced machine, the unbalanced force is, well, all of it, almost. So 90% is a number, and then the alarm limits below that are simply the alarm limits that we talked about a minute ago, times 90%. Whether it's in metric or English for the alert and alarm levels. So we have those same numbers for each of the 4 bands that you might apply. These bands, if applied, can be done entirely in the module. The module has 24 alarms that it can define. If we did 5 bands per channel, that's 20, so we can certainly do all of these plus the overall levels all in the module. So the controller need only monitor status information, so it's very, very simple. However, there are 8 bands that you can define per channel, so if you want to take advantage of that and monitor more indicators of fault, then the guide provides further information and guidance on, okay, if you want to use 8 bands, and then probably do the alarming of the controller, then this is what we suggest that you do as well. So in this case, we're going to monitor band 0, which is lower than 1x, bearing cage anomaly. So when we talk about bearing faults, one of the specific indicators occurs less than running speed. So we're going to monitor that. The other bearing fault indicators occur greater than running speed. So we do the lower than 1x, then we do the unbalance, and we do misalignment and looseness, and band 3 is also misalignment and looseness, but it's the 3rd order. Typically that's the differentiator, that if 2 and 3 are elevated, then it is more likely looseness. Band 2 only, then it is more likely misalignment, but it depends a little bit on the machine. Band 4 is vane pass, which indicates a problem with flow, which could be an obstruction or a problem with piping or something of that sort that is causing turbulent flow through the fan. Of course, it could be damage to the blades as well. bearing fundamental frequencies, this is the area right above 1x. It is indicative of the other bearing specific fault frequencies, those higher than 1x. And then 6 and 7 are the same as what we just talked about a minute ago. So this provides better information about what's going on with the machine. But it does require that if you do alarming, that you do it in the controller because the module simply doesn't have that many alarms. That may or may not be entirely true. If you do not use all 4 channels, then you could apply the 24 alarms in other ways. So in some cases, it would be sufficient. The Dynamics Application Guide can be a tremendous resource, not just in instrumenting a solution or defining the details of a solution, but also in imagining a solution, what could be done with the 1444 architecture. The Dynamic 1444 series is a unique product that, when made part of the integrated architecture, can make an extraordinary solution. There is nothing like it in the industry today. Use it to define how a machine could be monitored, how to create a smart machine. The application guide is available on the literature library. Simply search on 1444-AT, download the guide, and start making smart machines. Thank you.